Hello everyone. Today I'm going to talk about the single surface refracting interference. So it may be quite a long discussion today. Let's start with this. What I'm going to talk about is single surface, not a double surface. Like let me give an example. I'm going to talk about one surface. Let's take an example. This is the cornea, and we have two surface, front surface and the back surface. We are not going to talk about the lens itself. We are going to talk about the surface. If you consider the lens, we have two surfaces, front surface of the lens and back surface of the lens. And we're not going to talk about whole lens. We're not going to talk about whole cornea. We're not going to talk about whole contact lens. We're not going to talk about whole spectacle lens, but we're going to talk about the surface, because let me tell you one thing. The power lies always in the surface. Essential important concept you have to understand. Power lies in the surface. So let's take an example. This is the surface, only one surface, and this is again another surface. It has power of, let's take example of plus 10 diopter, and it has power of, let's take example, minus 6 diopter. If the thickness doesn't matter, this thickness doesn't matter, then we simply add the power, which is plus 10 minus 6 is approximately plus 4. This is how spectacle lens work. But if we consider thickness, then it's called thick lens, the where the thickness matters. Thickness influences the power of a lens. But no matter what thickness, there is thickness which is significant, or there is no thickness which is not significant, or something like that. In actual, in calculation of the cornea, the front surface is considered 48 and back surface is considered minus 6 approximately in general. So we take almost 42 or 43 diopter, because in case if we consider the thickness, which is basically 500 micrometer, then it gives approximately 0.5 diopter difference. So we don't consider it as a significant. In this case, we don't consider it as significant. So normally in case of spectacle lens, we don't consider the thickness is that much important. But if power goes higher and higher, then thickness matters, and then we treat that lens as a thick lens. But in case of contact lens, we treat as a contact lens as a thick lens, where thickness matters. In case of cornea, a little bit thickness matters, very little. So that's all. So as we have discussed in the previous class, that in case of surface, only one surface, that is single surface, we can tell the surface is converging or diverging, isn't it? So surface is either plus power, or surface is either minus power, or surface is either planar power, there is no power. So we can tell that. And the magical formula that we know, I think you guys also know, is n dash minus n divided by r. What is this? This is the difference of refractive index of the two media. What is this? The curvature of surface. And as I told you in the previous video, that the three things that matters when we talk about the power. First and foremost, the refractive index, change of the refractive index. There must be change of refractive index. Second, there must be a curvature. Third, thickness. So thickness also matters, but as we have discussed, thickness matters when thickness is significant. So thick lenses where thickness is significant. So in case of optometry, there's three things you have to understand. First, change in refractive index, it must be there. Second, curvature of the surface, it must be there. And besides from the surface, if there is two surface or multiple surface, then thickness, the separation of the surface, that matters. So today we are going to discuss about only these two topics, that is in the difference in index and the radius of curvature. So let's talk about the surfaces, that is convex and concave. So many of the students always do that simple mistake. Whenever they see this type of curvature, they call it convex, which means the plus surface. And whenever they see this type of curvature, they say it's a concave. You see convex, which is plus power, which is this is concave. I I would not say that you are wrong or something like, but if you see something like that and you tell this is convex and you tell this is concave, it will be a great mistake. Let me tell you why. Because convex and concave, I'll make you convex and concave. Let's take an example of this. So if refractive index of this media is 1.4 and this medium is 1, then definitely it is convex. But refractive index of this media is 1.4. Let's take it. This is a separate, and this medium is this. Now this is concave. This is minus power. This is plus power. So it depends where which medium bulges out to which medium. Are you getting the concept? So let's make example. In this case, this medium, let's take an example of 1.5 diameter, which is glass. This medium is bulges out towards this medium. Let's take an example of air. So now this is convex surface. In this case, this surface has plus power. Okay. So if you do same thing, it looks like this. This medium has refractive index of lower index, and this medium has refractive index of higher index. Then this surface is negative, which is concave surface. So it's central important to understand this concept. So let me explain with the help of cornea. So let's see. This is two surface in cornea. This is one and this is second. In case of the cornea, let's take an example of 1.39 is the refractive index of cornea. And here air and here aqueous. So if aqueous is bulges towards the cornea, which is lower index bulges towards the higher index, which is cornea, lower index, which is aqueous, bulges towards the higher index, then this surface, which is back surface, is a negative surface, isn't it? Minus 6. In case of this front surface, where this cornea is bulges towards the air, so that's why it's a plus surface, positive surface. So it's central important to understand why the posterior surface is negative and why anterior surface is positive, isn't it? The same thing happens in case of our spectacle lens. See, let's take an example. This is spectacle lens. Then the glass bulges towards the air, isn't it? And the air bulges towards the glass. If you see this surface only. So then if you see this surface only, the air bulges towards the glass, and in this front surface glass bulges towards the air. So this surface is positive, which is concave surface. This surface is negative, which is concave surface. This is convex surface. So this is a plus and this is minus surface. So it's central important to understand it's not about this. It's not about, so it's not about this shape or it's about this shape. It's about which surface bulges towards which surface. So let me make another clear example. This is very good example. So let's see. If this is a glass, let's take an example. And let me take another. This is blue bubble of air. Okay, this is a glass 1.5 index, and this is the air which is trapped inside the glass. So what happens there? There is a four surface, isn't it? The first surface, this surface, second surface, third surface, and fourth surface. You can tell that in this surface glass bulges towards the air, isn't it? So this is higher index bulges towards the lower index, so plus surface. But then in this case air bulges towards the glass, so this is negative surface. And again see, this is air bulges towards the glass, it's negative surface. And in this case glass bulges towards the air, so this is positive surface. So that's why we can see, we can understand that there is four surfaces, and all the four surfaces we have to see as a higher index bulges towards the lower index or lower index bulges towards the higher index, so that you can understand more and better way to articulate this concept. So this is very important concept to understand how refractive index change matters. Okay, so another which is very important concept I'm going to discuss is the concept of a sign convention. In case of optics, sign convention, it's very important. So let's take an example of this. So we always consider light travel from left to right, and this, let's take an example, this is the lens, this is lens. So simple, whenever we put object here, then we will take the object distance, isn't it? So we have to take object distance from the lens center, from the lens center. If we take object distance from the lens center and it travels against the direction of light, which is against the direction of this light, so then we take that distance in negative sign. And we, so let's take example, this is the image, then always image should be taken from the lens itself. So let's take example from here to here, it is same in the direction of light, so we take a distance in a positive. So it's central important to understand why we take a distance as a negative and why we take distance as a positive. We have to take distance from the lens, no matter what. You remember this point, because my students, all the students in optometry always does this simple funny mistake. They take distance from the image towards the lens, and they say, sir, this is how it happens. This is not how it is. And if we take the distance from image to this, then this distance is negative. It's not like that, you cannot do that. You have to understand the distance you have to take from the lens towards the image, from the lens towards the object. So let's take an example. If this is the lens and this is the light distance, if object is here, so let's say example virtual object, isn't it? If the virtual object is here, then we take a distance from lens towards this, then isn't it, this is a plus because it's towards the light, direction of light, not against the direction of light. Let's take example, this is the image, then we have to take distance from here, and distance must be negative. And another simple example, of the height of the object or image, which is erect, is positive towards the y-axis, and inverse is negative if we take height of the image, which is simple. So there are two things that you have to understand a lot, and we will definitely move forward with another relation with the calculation of uh, that single surface refractive interference, and we will definitely move forward with the single surface refractive interference calculations in the next video. If you want another topic, so that you won't tell me that if you want another topic, this topic, please make a video of this topic, then you can tell me in the comment. Okay, bye bye.